Hi, and welcome back to another Dresner Academy video. In today's video, we're going to be going over reaction mechanisms and their corresponding energy diagrams, specifically this two-step reaction mechanism here. So we're going to start with this reaction. Now we have our reactants, we have our products drawn out, but what I want to look at is the flow of electron that occurs between these steps. So we know that here, S and O, sulfur and oxygen, are more electronegative than carbon. Their electronegativity is going to draw electron density away from the carbon, and it's going to make this carbon partially, let's make this marker a little smaller, it's going to make this carbon partially positive, okay? And it's going to make this carbon our electrophilic center. Now, NH2 is going to act like the nucleophile in this situation. So we know that opposite charges attract, so this NH2 is going to use its lone pair and bond to this carbon. So I'm going to go ahead and draw this nucleophilic attack from this lone pair onto this carbon here, all right? And the next thing that's going to happen is we're going to break this bond here, this pi bond, and these two electrons are going to come off onto this oxygen, and it's going to give this oxygen the negative charge that we see here on this next step. So next, we're looking over here, and we see that we have this next negative charge. So this negative charge is again going to be attracted to this slightly positive center. Now I'm not going to draw it, but we can assume that this center is slightly positive. So this lone pair, which we can't see, but I know that there's a lone pair here, is going to again reform this pi bond, this double bond here. And again, we can't have carbon having 5 bonds, so one of these is going to break. Which is going to be our leaving group. So one of these bonds is going to break. We know NH2 is a strong base, so if you kick this NH2 off again, it'll just attack the nucleophile and we'll be back to where we started. But if we kick this sulfur compound off, it's not as reactive and it can handle this negative charge. So that's what we're going to do. We're going to draw an arrow showing this bond breaking, and these electrons are going to go back onto this sulfur, giving this sulfur a negative charge. Alright, so now that we have our electron flow drawn out, we're going to take a look at our energy diagram. Now before we jump right in, let's give ourselves a little outline sketch. We're not just going to go ahead and start drawing squiggles. So the first thing I want to look at is I'm going to look at the difference between our reactants and our products, because those pretty much give us a really good sense of what this is going to look like. So in comparing those, I'm going to look at the most reactive piece, which is this here, this NH2, and on this side, this sulfur compound. So what I'm trying to figure out is which one is lower in energy, because we want to decide which one is the better leaving group, meaning which one is more stable on its own. So basically, a weaker base is a better leaving group because it's less likely to react again. So in this situation, sulfur is bigger in atomic size, so there's more distance between the electrons and the nucleus, and it's also more polarizable. So it's better at stabilizing the negative charge that we have here than this NH2 is, meaning that it's less reactive and therefore a better leaving group. So therefore, our products are going to be more stable than our reactants. And we're going to go ahead and draw this here. So our products are going to have less energy than our reactants. So I'll go ahead and label this as our reactants and this as our products. So next we're going to be looking at this step, which I'm going to label here as our intermediate. So this is our intermediate 1, which is in this situation our only intermediate. All right, and our intermediate step is going to be more unstable than both our products and reactants because of this negative charge here on the oxygen. It just inherently makes it more unstable. So I'm just going to go ahead and draw that right in between reactants and products, and also higher in energy, both of those. So before we start our next step, this might seem a little unrelated, but just go with me for a second. So picture a werewolf in your head, but a werewolf in his human form, right? Just looks like a normal man. Now when the full moon hits or whatever happens that turns him into a werewolf, he doesn't just poof into this dog, right? No, he transitions. And it's this grueling process, and you've seen it in the movies. His veins just pop out and he growls, and it's just this really unfavorable thing. Well, the same thing happens in mechanisms. There are transition states that occur between each step in the reaction, and they're really unfavorable and high in energy, and are basically the instant that bonds are on the verge of breaking and forming. So I'm really quickly just going to draw an example of what our transition states look like. So I've quickly went in and drawn out our transition states. Now in transition states, bonds are in between being broken and formed, so we have partial bonds. So we show this by using dotted lines like we have here and here, and these are our partial bonds. And then along with this, Formal charges on these atoms are partial because they are being formed or diminished. So for example, here this oxygen has a partially negative formal charge because it's not neutral, but it's also not negative. And we have the same thing here. While this S is being broken off, it's becoming our leaving group. It doesn't fully have this negative formal charge yet, but it has this partially negative charge. And then to top it all off, we label these transition states with this symbol here to signify that transition states are temporary. Now let's get back to the big picture of drawing our energy diagram. It's not just as simple as drawing a slope between our reactants and products, right? It's not just as simple as going from human to wolf, you know? It requires a lot of energy to do these transformations. So I've come up with this little trick for transition states. So basically, if your reactants are higher in energy than your products, your first transition state is going to be higher in energy than the second one. This pattern typically stays true for most mechanisms. So if you're ever in doubt, just use my handy trick. And now we can just draw this first transition state, which I've labeled here, as higher in energy than our second transition state. And both of these are going to be also higher in energy than our reactants, than our products, and our intermediate states, just because it's such an unstable thing to be, right? Think of that werewolf. He's unstable, and there's no other way to describe it. So now we get to the fun part. We get to connect these dots here. So we go straight from our reactants. We're in this energy field, right? And then we're breaking and forming these bonds, so our reaction goes way up, right? We're super unstable. Now these bonds go back down. They formed, right? But it's still not as stable as it could be. And then we form more bonds, we break more reactants, we go back up to that second transition state, and then now we go back down. We're at our most stable point in the reaction, we're at our products. So that's it. This is our Gibbs free energy diagram, and this is our mechanism, and these are the steps. So if you're ever in doubt, just remember that the transition states follow the same pattern as your reactants and products. So I really hope you guys had a good time, hope you had fun, hope you learned a lot. I had a great time. Thanks for watching, and I'll catch you next time,